Okay, so yes, all week you have been fitting models to data, which is great. And now finally, at the very end, we will say a few words about how do we know if that was worth doing? Is the model actually any good? So specifically, under the general heading of model evaluation, you can think about these three questions. The first one, does a model actually describe the data well? And let's keep in mind, when we say model, I am talking about generative models. So this is the thing that tells us the entire process by which the data were produced, right? Does that actually describe the data that we got? Number two, does it make accurate predictions about new data? That may or may not be something that you actually care about in and of itself. It depends on your application. But that can be a useful metric for saying, is model A better or worse than model B? So it's something to think about. And then there's also getting right to the meat of it. How probable is model A compared with model B given the data? So those are all things that we will hopefully touch on in 43 minutes. Okay, yes, repeating what I already said, but more specifically, model means everything. That means that when I say model, I'm including in model specification the choice of prior. So two identical PGMs, let's say, with the same relationships between physical universe and data, if I choose a different prior for some parameters, we're going to call that a different model. And the thing you can have in mind there, the example that we'll look at, is I have some parameter, and in one case, one model, I have a great big wide uniform prior, and in the second model, I've put a sharp Gaussian prior on it or something. We're going to call those different things because I've added different assumptions into them. So here is a familiar example that you are sick of. Y versus X. We know X. Y is something, and there are Gaussian error bars. And you'll be thrilled to know we're going to fit a line to this, because why not? So precisely known X values, Gaussian errors on Y. We will fit a linear model. You can probably guess by eye whether that's going to work very well. And that's a perfectly legitimate model evaluation technique. But we'll do more than that. How can we say whether that model is any good? I'm not going to make you watch as I fit it. So it's been fit. Here's the posterior distribution, some plots on the left. And on the right, it's the data with a bunch of lines drawn from the posterior distribution on there in semi-transparency, as we are used to doing. And this is always a useful thing to do, just with your eye, compare models that come from the posterior with the data. So again, even without doing any fancy math, you can probably guess what our conclusion will be, but we'll go through the exercise anyway. In fact, for this specific case, it is worth pointing out, so linear and Gaussian errors, a lot is known analytically with pencil and paper. So in this case, the likelihood is e to the minus half chi-square, where chi-square is the usual sum of data minus model over error bar all squared. And if the priors on intercept and slope are uniform, then priors are constant, multiplying e to the minus half chi-squared likelihood. So that's also the posterior. Which brings us to classical hypothesis testing, something that you have probably seen in one form or another somewhere in your education, but we'll just go over it quickly again. So again, in this specific case, linear and Gaussian, we can say if we assume that model is correct, we know something precise, mathematically precise, about the distribution over data sets of the best fitting chi-square value. So imagining this model could produce many slightly different data sets as it can through the measurement errors, we can make a precise prediction for what we would get for the best fit chi-square over many different data sets. Irritatingly, that distribution is also called the chi-square distribution. So talking about overloading the letter P, we also overload the letter chi. That distribution has one parameter, the number of degrees of freedom, and the appropriate number for this is right here, the number of data points minus the number of parameters. So what we can do, logically enough, is compare that precise mathematical prediction for the distribution of best fit chi-squares over data sets with the best fit chi-square value that we actually got for the one data set that we have in reality. And we can just ask, does it look like this thing that we got is a sample from the predicted distribution? If it is, it's reasonable to conclude that perhaps this model is the one that generated the data that we have. And if it isn't, then it probably isn't. That's the logic. And here's what it actually looks like in this particular case. What we get for the best fit chi-squared is 104. This is the prediction for 28 degrees of freedom. And it doesn't look particularly likely, just by eye, that this number is a draw from this distribution, does it? Okay, but to make that quantitative, we would look at what's called the p-value or the significance. This is all from classical non-Bayesian statistics. And what that is simply defined to be the area under this distribution to the right of the value that we actually got, which is like not even visible here. So the probability that something drawn from this distribution would exceed the particular value that we got, it turns out in this case to be like 10 to the minus 10, which is a very extreme value, right? That's just in a number telling us that we live way out in the tail. If the p-value were 0.99999999999, we would be way over in this tail. That also would not indicate that our value was very likely to come from this distribution. But if it were of order 0.1 or even 0.01, then it's not ridiculously unlikely, right? It's somewhere in this place where you can actually see the chi-square distribution. So in classical statistics, let me skip over some of this. What we would have said is, beforehand we decide what kind of confidence level we would adopt in order to say that a model does or does not fit, if it's 95% or something. And so in this case, we would say our p-value is 10 to the minus 10. That's less than 0.05. And so this model is ruled at the 95% confidence level, and actually much greater than that. So all of that is wonderful, and I encourage you to use it if your model is linear and Gaussian. But that's not most models. Despite all of the line fitting that we have done this week, there are lots and lots of cases where all of the assumptions that are required to use the chi-square distribution are not exactly right. We'd like to do Bayesian analysis. We're not always going to have this situation. So we can still do something which is very, very analogous. So the way that we do that is choose a test statistic. That means some function of the data that I can calculate, and hopefully it's something that somehow describes a feature of the data set that I would like the model to fit well. So we can do that. We can calculate it for the data set that we have, and we can go through a very similar logical path to fit our model, take samples from the posterior. From those samples, use our generative apparatus to produce mock data sets. We can calculate the test statistic for each one of those and empirically build up a distribution of what the test statistic should look like if our model is correct over data sets. And we can do exactly the analogous test. So that distribution that you build up is called the posterior predictive distribution. Lots of words here that I've already said, so let's skip that. One choice, this is not the only choice, but a test statistic that you might choose in this case is the correlation coefficient. This is the empirical correlation, just telling you how linearly correlated are x and y. So this is only a function of the data in this case. And we'll just go through this procedure. So I showed you the model fit for the line. If you generate many mock data sets from that posterior, calculate the correlation coefficient, then what you get is this blue histogram here. And what we get from the real data is this vertical line. And so again, we're sort of out here in the tail. Interestingly, we're not quite as discriminating in the sense that we're not ruling out the model as definitively, right? This is not 1 minus 10 to the minus 10. This is only 0.995 or so. And that's probably because the correlation coefficient isn't the absolute best test statistic. I mean, this is a case, again, where we have beautiful mathematical analytic results that are maximally powerful. But in general, you wouldn't have those things, and so you would do something like this. And again, you would probably say, it doesn't look like this data set came from a linear model, right? Oh, yeah, just some features that are nice about this. Because we are sort of iterating over posterior samples as we do this. This naturally accounts for the width of the posterior. We're not just going to do this with the maximum likelihood fit, for example. And because we're producing mock data sets, it also accounts for the error bars because those are going to go into the mocks. Okay. So that was an example where the test statistic was a function of data only. It is also possible to have test statistics that depend on both the data and the model parameters. And the best fit chi-square is actually one example of this, right? It's data minus model prediction divided by error bar. That's okay. In the more general case where you don't have an e to the minus chi-square likelihood, the log likelihood itself, or the maximum log likelihood, is a perfectly good choice, and one that one doesn't have to really think very hard about because we always have a log likelihood in our problem. So in this specific case, of course, the maximum log likelihood is almost identical to the minimum chi-square. And so we'll find exactly the same thing that we saw analytically before, but nevertheless, if we go through the process anyway and mock up many data sets and make a histogram of the maximum log likelihood, now there's a minus sign difference, so, oh, actually, no. This must be a histogram of minus the maximum log likelihood. But in any case, this looks very similar to the curve that I drew earlier, where we knew the actual chi-square distribution, and we were way out here at a much larger best fit chi-square. So this histogram, I'm going to guess, has many fewer than 10 to the 10 mock data sets going into it. It's pretty reasonable then that the empirical p-value, in other words, the number of simulated best fit log likelihoods that exceeded the one that we got from the data, is actually 0. And we could never, on the basis of this, come up with a p-value of 10 to the minus 10 just because you'd need a ridiculous number of samples to do that. But we can certainly say that it's not likely that that observed number came from the predicted distribution. Forward. Okay, so regardless of exactly how we do this or what test statistic we choose, as long as it's reasonable, in the case that I'm using as an example, we would probably conclude that the linear model is not a good explanation for how the data came about, right? So naturally, what we would probably like to do is find a model that does a better job. And so that brings us to the next task that we have, which is how do we choose among different models? And one way, as I said, that we can think about that is by answering the question, how accurately does a given model predict new data compared to a different model? Which brings us to information criteria. So some general thoughts here. You've seen a bunch of examples this week of fitting really high order polynomials to data, right? And as you increase the order of the polynomial, if you're not doing ridge regression or something like that, then you get better and better fits, and eventually you have a curve that goes exactly through every measured data point at the expense of making what intuitively appear to be completely ridiculous predictions at values of x where we don't have observed data, right? You wind up with these huge oscillatory high-order polynomial functions that happen to go through the data that we have, but if you make a prediction somewhere else, it looks crazy. Which is just to say that what we would like in a criterion of this sort is something that balances the goodness of fit with the model complexity. In other words, there's some penalty that prevents us from overfitting in a way that gives us all that crazy behavior, which is something that naturally comes out of this idea of predicting new data well, right? So in our example, a logical next step in the absence of any actual physics that we're trying to understand would be fitting a quadratic model. And here you can see what happens when we do that. Visually, it looks much nicer. If we do this discrepancy measure test, the test statistic test, all of a sudden it appears very plausible that the data set came from a quadratic model. They didn't actually come from a quadratic model, but nevertheless it looks plausible, right? And we don't know what the right answer was. So how do we quantify how much better that model is than the linear model? So if we're talking about predictive accuracy, then the gold standard would be to actually get new data, and then you can calculate the log likelihood or whatever for the new data on the model A and model B, and you can see which one does better. But it's very hard to get proposals through on the basis of just doing this. I mean, it is a very good reason to get new data, but usually attack would want to see evidence that you've done as much as you can before using a telescope, right? So the next best thing is called cross-validation, and the idea there is basically to take the data set that you have, break it up in many different ways, and for each of those ways, you fit your models using a portion of the data, and then the remaining data you treat as though it were new data. And so you can sort of do this test of how well the prediction works for new data in a not quite perfect way, in the sense that all of the constraints that you get within this process will be less tight than they would be if you use the entire data set. But nevertheless, in terms of comparing how well each model does, this is a way of doing it. That is, of course, very computationally intensive, depending on the model that you're fitting. And so, moving forward, if you'd rather not go to that expense, then you have these things called information criteria, which approximately asymptotically give you the same answer as cross-validation. And when I say asymptotically, what I mean is, if you do a lot of math, which I'm not going to pretend that I've done, you go to the limit of having the linear Gaussian model, then all of these things give the same answer as chi-square. And if you have a different model, well, it's not exactly the same thing, but they're more or less measuring what we want, which is how much does the fit improve versus how much more complexity did we have to add to the model. So there are a bunch of them, and this is not a complete list. I'm only going to say anything in detail about this one, the Deviance Information Criterion, or DIC, which is pronounced DIC, just to be clear. So the reason for liking this one a little bit better, and this is an opinion, just to be clear, is that, for one thing, it is compatible with sort of the Bayesian approach to doing things, which some of the older versions are not. And it's kind of easy to calculate. You can always do it. It doesn't get weird if you have complex and hierarchical data or anything like that. So here's the formula for the DIC. First of all, capital D, we call the deviance. That's just -2 times the log likelihood. Likelihood, not posterior. So this is in terms of the likelihood. Although it is compatible with the Bayesian viewpoint, this does ultimately come from a pre-Bayesian sort of thing. It's a modification of an earlier information criterion, so it looks at the likelihood. The angle brackets mean averages over the posterior. So the DIC is the average over the posterior distribution of the deviance, basically of the likelihood, plus twice this thing called P sub D, and that is that same average again, minus the deviance evaluated at the average parameter value under the posterior. So a couple of things. First of all, this is stupidly easy to calculate if you have done a fit with Markov chain Monte Carlo and you have samples of the posterior, assuming that you bothered to record the likelihood value for all of those samples, because then this thing is literally just an average of your samples. And here, well, you can calculate this easily as the average of the parameters over the samples. It's just the centroid in parameter space. And, maybe you have to evaluate the likelihood one more time to get the deviance at that exact point. So it's not a challenge if we're already doing a model fit the way that we're used to doing it. We don't have to do very much extra work. Now, clearly, this could be written in one go. We don't have to separate this PD. But the reason for doing that, partly it's to make it look like other information criteria, but partly there is a meaning to this PD, which is not necessarily obvious from the formula. So PD is something like an effective number of free parameters. What does that mean? This is the connection to the Bayesian-like interpretation. So if I have, of course I always know how many parameters I'm varying in my fit. But there's a difference here between a parameter which is very unconstrained by the prior and one which is highly constrained by the prior. Just intuitively, we're building in much more information in one case than the other. If we have a parameter with a very wide prior, not constrained a priori, that's kind of like the classical statistics case, right? We're not saying anything about it. This parameter can adjust itself however it wants to best fit the data. If we put in a prior which is very sharply constrained, there's really not a whole lot of freedom there. It shouldn't count as a whole new free parameter in that sense. So again, not obvious from the formula why it should have that interpretation, but it's frighteningly good at reflecting the number of actual degrees of freedom that you have to play with to best maximize your likelihood. And we'll see a little bit an example of that in a second. Okay, the way that these things are defined, just as a practical matter, lower values, especially, just going towards negative infinity is what I mean by lower. Lower values mean the model is doing a better job. So it's kind of annoying how to see it. Remember that deviance is minus the log likelihood, so lower means higher log likelihood or smaller complexity in terms of the number of effective parameters, right? Either one of those things. This is just to mention there is something that you can point to once you have evaluated this for two models and taken the difference. You can say, based on this guy, Jeffries, who came up with the scale, is this decisive evidence for one over the other, or strong, or so-so. Okay, so let's see how this works in a sort of limited way, at least. This is the simplest thing that I can come up with. So let's imagine we have a model with one parameter, theta. The likelihood is just a standard normal, so it's Gaussian, mean of 0, standard deviation of 1. The peak value is something like 0.4, I think. It doesn't really matter. And remembering that a different prior means a different model, we'll just look at these three cases. So prior uniform between -1 and 1, uniform between large numbers, so effectively minus infinity and infinity, and then uniform on a kind of a small range that doesn't actually include the peak of the full likelihood function. So here's what we're going to do. I'm actually going to do A for you. I'll sketch the likelihood and the priors on the board, and while I'm doing that, think about how these different quantities compare to each other. So we're actually going to make a little table that has this thing, and PD, and the DIC for these three cases, and do not think about getting precise numbers for these things. In fact, all we're really looking for is, for this one, in case 2, is it lower or higher, bigger or smaller than case 1? Because the actual calculations are a little bit annoying for the DIC. So have a think about that, talk to the people next to you, all of the usual stuff, and I will be drawing on the board. All right. Keeping in mind, we only want very broad qualitative things to say here. Hopefully that's enough time. So let's just think about this stuff. So first quantity here, average of the deviance over the posterior. Keep in mind the posterior basically looks like the white likelihood curve here, but truncated at whatever the bounds of the posterior of the prior was, right? So how does that compare between the three cases? Let's say this one, -1 to 1, this is going to be the baseline. So if we have the wider prior, how does the average of the deviance of the posterior compare? Or let's say likelihood. How does the average likelihood compare? I heard a word. It was sort of whispered. I think it was smaller. Okay, so the likelihood, yes. If we take the average of this thing here and the average of the entire curve, of course the likelihood is going to be smaller. So the log likelihood will be smaller, so -2 of that will be bigger, closer to 0. Yeah, all right. This is going to confuse me, this negative sign, but you can help. Okay, so bigger. Okay, and now over here, we still have a small prior, but it's in this part of the tail, so that will look like what? It's not 100% obvious, actually, at least to me. But it will still definitely, it will wind up being bigger than the first case for sure. Let's leave it at that. Okay. Deviance at the mean parameter value within the posterior. That should be much more straightforward. Again, let's say this is the baseline. What do we have in this case? Okay, question 2A. Where is the mean of the posterior parameter space? Here versus here. Sorry? The same, right? Both at 0. Because in both cases, you're getting something symmetric about 0, and that's where it's maximized, so the same. And in this case, it will, of course, be somewhere in here. And so it will be smaller. Sorry. Likelihood will be smaller, deviance will be bigger. Good, thank you. Let's just say big. Okay, so cheat sheet. So PD is the difference between these two things. So this is our baseline. Here we have bigger thing minus baseline, so PD will be bigger. Here we have bigger thing minus bigger than that one, and so it will be smaller than this, but we're not sure about how it compares to this necessarily, right? Okay. Yeah. Okay. We will fill this in with an actual calculation in a second. Okay. And then the DIC is this guy minus this guy. So here it's not actually clear, is it? Or here. Okay. When we do the equivalent thing with the evidence, we will be able to fill everything in without having to resort to a calculator. But I thought it was worth at least thinking about this stuff a little bit and visualizing, taking the average within these boxes and that sort of business. Okay, so all of the things that you would need to do to calculate this in this case, I'm sure are analytic, but I was lazy and did this at like 9 p.m. last night, so I'm actually getting samples from the truncated Gaussian and doing it. So let's just do it, and we have to wait for imports and that sort of thing. Okay, so this is actually printing out numerical values for all 4 of these things here. And let's just copy over. So the DIC for the first one was 2.7. The second one was 4.8. And the third one is 12.8. Okay, so remembering that more closer to minus infinity values are better. If we're here, so our prior includes the actual likely values, then we're at this value. The absolute value means nothing. If we are spanning the entire range, then we have a larger value, so that is not preferred. And the reason that it's not preferred, actually, we should also look at the PD values. The reason it's not preferred, presumably, is here we have a staggeringly close to 1.0 value for PD, number of free parameters. And here we have like a third of a free parameter, because we've constrained it. So it's presumably that Occam's razor effect, which is killing us. And here, for whatever reason, we have like 7% of a free parameter. It's not obvious immediately why it would be different from this, but it is. But mainly what's killing us compared with Model 1 is just the fact that you're all the way out in the tail here, and the likelihood is terrible by comparison. So hopefully qualitatively, at least, this makes a certain amount of sense. Basic conclusions here are models that are less prescriptive in terms of priors are penalized for the reasons that we said. But there is, at least to the extent the PD does what it says on the box, there's a limit to this. You can add a parameter, and then at maximum that's 1 free parameter. And so if you've got that penalty, but the improvement in likelihood is large enough, then great. That wasn't the case here because we weren't getting better likelihoods. We already had that in case 1. Okay, we are running a little bit low on time. But let's see how far we get into the actual evidence. Then maybe we can continue after the break for like 5 minutes. Okay, so here's the third question, the one that should be appealing to the Bayesians in the audience. Forget about all of this predictive accuracy stuff. I just want to know how likely is this model versus this one, and I have this data, right? So not a question that you see in classical statistics. but Bayes' law can be applied to this just like it can be applied to basically any question. So, reminder, this is Bayes' law for parameter inference, and the only difference here from the way that we usually write it is I'm, again, explicitly putting our model assumptions here with the letter H for, I guess, hypothesis. But as usual, D is data, theta are parameters. However, there is absolutely nothing that prevents me from writing this version of it, which would be for inference over models. So the idea here is omega is some kind of master list of models that you could conceive of, and H is a particular one, and D is data, and all of these terms have exact analogs above. It's a true mathematical statement. So as usual, what we do immediately is throw away the denominator because that's hard. It is turtles all the way down, right? However, in this case, the equivalent of the likelihood is P of data given hypothesis. This is what was in the denominator for parameter inference. This was the evidence, the thing that on day one we said was important, but we're going to forget about it until Friday, and which is apparently hard to calculate. So this is our evidence again. This is an integral over the parameter space of the posterior, or you will also hear it described as an integral over the prior of the likelihood. These are the same thing, it's just this expression. And the other difference is that now we have a prior for the model. And as much as people sometimes really hate having to define priors on parameters, they really, really, really hate having to define priors in model space. It's just a thing. It's a psychological human feature. I don't know. Nevertheless, we should, in principle, compare models by looking at this posterior for each model, which of course is just the ratio of evidence times prior. General difficulties in doing this. Getting people to admit that they have priors on models. Just staggeringly hard to do. People always want to say, well, they're more or less the same, no matter what. And even if they've seen the outcome of the comparison already, they still tend to not want to throw away models. Problem number 2, assigning priors to parameters. If all we're doing is parameter inference, and we've done this over and over again, you've heard things like, well, if my prior is a lot wider than the likelihood, it doesn't really matter what it was, right? If it's uniform and we have bounds that are wide enough, they can be plus or minus infinity or anything. That's no longer true if we need to calculate the evidence. So you need to actually define a prior that you can stand up and defend in some way, as difficult as that can be. And then finally, actually doing the calculation. However, that last part, at least very intelligent people have figured out methods for that we don't have to code up ourselves. So let us do the same exercise again, and this time I claim that we don't need to resort to the calculator necessarily. So same thing. The likelihood is the standard normal. We just have theta. We have the same 3 different priors. And we just want to know, how does the evidence compare amongst the 3 of them? So think about that with your neighbor for a couple of seconds. All right, let's come back together as a group and collectively make sense of this. So this one is, again, I claim, much more straightforward to think about than the DIC case, just because the calculations are less complex. So I'm going to be the annoying guy who stands there with a piece of chalk until somebody talks. For case number 1, what is the evidence, roughly? Integral of likelihood times posterior over theta. Sorry, of likelihood times prior over theta. This is, I mean, I say we don't need to be too quantitative. Depending on how much you've worked with Gaussians, you might know the answer to 2 significant figures already. It isn't 1, I will say. But so think about the function that we're trying to integrate is the product of the white curve and the green, I guess, box here. So 0 out here, 0 out here. It's not the full integral of the Gaussian, right? Over the whole line, it would be 1. but between these two bounds. So the integral of just the white curve from -1 to 1 is 0.68. And what's the value of the prior? Uniform from -1 to 1? Uniform from -1 to 1, value would be 1/2. Right, because it's got a width of 2. Yes, everyone, including me, has made that mistake. It's okay. Okay, so to two significant figures, the evidence for case 1 is 0.34. And the rest will probably not be as nice. So let's see. Let's call that the whole real, well, okay, no, we can't call it the whole real line because then then the prior would be 0. So -100 to 100. Somebody help me out. We can say the integral of just the likelihood from -100 to 100 would be 1. That's fine. Which means we just have to take this function and scale it by whatever this prior is and do that integral, right? So what's the value of the prior from -100 to 100 uniform? 1/200. Right. So we have 1/200 out the front of the integral of a Gaussian, basically -infinity to infinity. So it's 1/200. Whatever that is the answer. And you're all sitting in front of calculators, so you can tell me whether 1/200 is larger or smaller than 0.34. Yes. It's a small number, yes. Okay, and the final case, we have also a prior whose width is 2, but it's all the way out here. Okay, this one we're not gonna easily get a number for, I will admit. But it's definitely smaller than this guy, right? Because it's the same prior, and it's multiplying a likelihood which is smaller. So let's fill in all of the numbers. And as promised, this is a simpler thing. It's one line. Okay, so indeed 0.34, 0.005, and let's say 7 times 10 to the -4. So does this make sense to us? Case 1 versus case 2. We have a lot of prior information here and not much prior information here. So we're being penalized for adding additional complexity to the model. And we're not doing any better as far as the best fit. That's a simple way of thinking about it. So that's a big penalty in the evidence, right? 0.005 versus 0.34. In the third case, we're being just as prescriptive for theta as in the first, but the likelihoods are terrible. And it's an even bigger difference. And then between 2 and 3, those are both kind of terrible, but 2 is still better, right? It's much less prescriptive, but at least you actually get to see decent likelihoods within the prior. So there's a little bit of a lesson there, as before. And as before, models that are less prescriptive are penalized. It does mean that there is this sensitivity to the prior volume. So it doesn't mean that you have to spend an entire PhD thesis deciding what your priors are, but whatever you choose, you should put at least a little bit of thought into it, right? But there's only a linear dependence, at least in this uniform case, on the size of the prior. Whereas the likelihood, well, there's an exponential dependence on the log likelihood, which is the other term there. So basically, as we saw between 2 and 3, even though we were much less prescriptive in case 2, the fact that we could get to much better likelihoods meant that it was a better model in terms of the evidence. Okay. All right. There's just a couple more things to say which I could skip, but let's try and fit them in 15 seconds. This Bayes factor or odds ratio is a really weird thing. Basically, I would argue the best thing to do is look at the ratio that we saw before, the ratio of posteriors for models. But of course, people get very uncomfortable anytime you ask them to put a prior on something, and they get really, really uncomfortable when that thing is a model. And so the odds ratio or Bayes factor is kind of this bizarre attempt to apply frequentism to a Bayesian evidence. and ignore the prior part and just look at the ratio of the evidences, which of course is equivalent to having the same prior on both models. So it's just to mention, this is the thing that people do. You can, skipping, somewhere in there. Well, anyway, you can interpret it in terms of, yes, here it is, the same sort of Jeffrey scale as we used for the information criteria. So I shouldn't be too cavalier about it. There are asymptotic proofs and things that make the odds ratio a nice thing from that point of view, so you can have that connection. But it's still kind of weird to interpret compared with just a posterior density, right? All right, finally calculating the evidence, something practical in -1 minute. There's not much to say about this because we're not going to dig into the methods really. But it's worth saying, so estimates calculated directly from Markov chain Monte Carlo samples of the posterior generally don't do well for calculating the evidence. And that's because the evidence is an integral over the entire prior. And if your model is constrained, then the posterior doesn't cover the entire prior very well. So this method, which is sort of optimized for getting samples of the posterior, where the posterior is large, naturally does very poorly where the posterior is small. However, those portions of parameter space can still contribute significantly to the evidence. Nevertheless, there's other ways of doing these integrals. The point is just that it doesn't, unlike the information criteria, this doesn't come for free once you've done the MCMC to get your posterior. That's all. It's a different calculation. So we saw nested sampling. You used nested sampling earlier. This is a slightly older code, which is harder to use than Dynasty, so I should add Dynasty there. There are these methods available to you. Okay, closing thoughts, I guess. Bayesian evidence is sort of different from the other assessments in that it comes from Bayes' theorem, and therefore it actually answers the question, which thing is more probable, if that's the question you're interested in. For the same reason, there's no inherent mathematical limitations to it. If you can actually define priors in a way which is sensible, then you can use it, and if you can do the calculation. All right, so just summarizing the overall points, we had these 3 questions at the beginning. Does a model describe the data well? The way that we look at that, we look at posterior predictions from the model. Visually, we can have test statistics and discrepancy measures. Does it make accurate predictions about new data? We have cross-validation, which I didn't show you an implementation of. But it's straightforward if expensive to do, and you have information criteria which approximate that, which are much easier to use. And then you have this question, how probable are competing models? And there you have the Bayesian evidence if you are willing to use it. So that is the lecture, and I guess we have a break for some amount of time that Adam will tell us, and then there will be a shortish problem on this stuff. Or there can be questions also, sorry.
Before we break, any questions for Adam?
Yeah.
2 questions. So the first one is the reason that nested sampling works like to get the evidence is that it starts all the way kind of at the outside of the prior and works inward from there?
Absolutely, yeah. I mean, at the end of the day, the only way to get information about the entire prior region is to start out by spamming the entire prior region, and that's exactly what the nested sampling does.
And then the other question was you talked about like people don't like putting priors on models, and I guess I've never seen that, so I'm just having trouble visualizing what does it actually look like to put a prior on the model itself or a model itself.
Yeah. So the reason that it's hard to visualize is probably that the space of models is not, it doesn't exist on the real line. But if you just think about having a list of alternatives, you could assign a relative weight to each of them. How much do you believe this before having seen the data? So, for example, not necessarily the best example, you could have one model which says the universe has exactly spatially flat, and your alternative model allows the curvature to be non-zero. Those are actually nested within each other. So the weights that you would put on those basically come down to how much do you happen to believe that inflation gave us, incredibly precisely zero curvature. There was a question up there. Mm-hmm. Um, so yeah, so the f-test is another example of one of these classical things, and I would say if you have a model for which the assumptions that go into the f-test hold, then absolutely use all of that machinery because it's incredibly fast and it's exact, right? And then there's the question, can you use it elsewhere? And this goes for chi-square testing as well. And it's not entirely comfortable for me to say yes, but there is this thing called the central limit theorem, which often holds approximately. And when it does, what it means is that effectively you are sort of making your way back to this linear Gaussian type situation to the extent that the posterior is close to a Gaussian. And then those tests can be, at a minimum, a really convenient and fast way to get some idea of whether one model is better than the other. And you see it actually quite a lot in the literature. Yeah?
The data that we fit the line and then the quadratic to, what were they actually drawn from?
So I didn't generate them, in fact. I'm pretty sure it was actually just a piecewise linear thing, which was contrived to look like it could have been quadratic. Yeah.